Hello everyone, and welcome to the second session of this set of videos created to explore programming applications in reinforced concrete. In this second session, we will be using Maple again, and we will explore a Maple document that is created to perform flexural analysis of rectangular doubly reinforced concrete beams. Doubly reinforced means that there are rebars in the tension and compression zones of the cross-section, whereas singly reinforced means that there are rebars only in the tension side of the cross-section. Again, I am assuming that you are familiar with the basic terminology of reinforced concrete. Doubly reinforced beams require a more elaborate analysis, as the compression steel has the option of reaching or not reaching the yield stress. Let's look at the Maple document that I created for the analysis of doubly reinforced rectangular concrete beams for flexure. This is the region where the user inserts the required input parameters, which are explained here in the figure. These parameters are the depth of beam, width of beam, yield stress of steel and compressive strength of concrete, number and diameter of bars in the tension layer farthest from the neutral axis, number and diameter of bars in the second layer of steel in tension, number and diameter of bars in the compression steel. N cycle is the number of cycles required for the iterative procedure to calculate the stress in the compressive steel Fs prime. Show cycles is a yes or no parameter, which is used by the user to decide whether to show or to hide the iterations used to obtain the value of the stress in the compressive steel. Concrete cover and the diameter of the stirrup. If we run the Maple file, Maple produces the required results. Let's start from here, where we can see the calculated values. Again, in this session and for simplicity, I'm just plotting out the variables. In subsequent sessions, I will show you how to format your outputs so that each number will be well printed and will have units right next to it. Maple calculates the required output parameters and decides that the compressive steel did not yield, and thus we need to use the iterative procedure to find the value of Fs prime. We indicated at the top that we do not wish to see the iterations of the iterative procedure, and that's why Maple here is saying after 15 iterations the values are printed as follows. Maple will show only the final results of the iterative procedure here. Maple will then print the nominal moment, check whether this section is tension controlled or not, and if it is tension controlled, it will print the design strength of the cross-section. After that, Maple will also show the plot of the cross-section, where we can see the tension steel in two different colors and the compression steel. Maple will also plot the ductility figure of the cross-section, where we can see from the blue dot here, which represents our location or the status of this beam. We can see here that we are well in the tension controlled zone, and thus the beam is accepted according to the ACI requirements. Also, Maple plots the convergence figure that shows the results of the iterative procedure. This here is the guess value, which is the trial value that we need to start our iterative procedure from. Then, as you can see, at iteration 1, 2, 3, 4, 5, and so on, we get closer and closer to the exact value of the stress in the compressive steel. The iterative procedure used to obtain the stress in the compressive steel is not the only way to do so. There are other methods, but I like to use iterative procedures and numerical analysis and incorporate them in structural engineering whenever I can. I will go to the top to the input parameter zone and change some of the input parameters and see what happens. I will change the number of bars in the second layer of tension steel from 2 to 4. I will change the number of cycles to 10. I will change the show cycles parameter from no to yes. And I will run the Maple document. Again, Maple produces the required output. Now you can see here that Maple printed the output parameters. In this beam, the compression steel did not yield, and thus we will be using the iterative procedure. This here is the trial value or the guess value. And now you can see that since we have requested to see the results of the iterations in this example, Maple plots the first table here, which includes the results for A, C, epsilon S prime, and Fs prime. And you can see that these values are formatted. I have given each and every one of them the suitable number of decimal digits for display and presentation. In the second table here, you can see the same results but without any approximation. These numbers without any approximations are used to produce the convergence plot at the end of the file. You can see that in this particular example, Maple printed the nominal moment. Maple checked the status of the beam and confirmed that the beam is tension controlled in order to print the design strength. Maple also plotted the cross-section, the ductility status of the beam, and the convergence plot of the iterative procedure. Let's do an interesting comparison. Let's solve this example shown on screen by analyzing the same beam twice. In the first analysis, we will disregard the steel in the compression zone by assuming it to be hangers placed to hold the stirrups in place. Neglecting the steel in the compression zone renders the concrete beam as singly reinforced. In the second analysis, we will take the steel in the compression zone into consideration, and we will analyze the beam as doubly reinforced concrete beam with AS prime consisting of 3 bars 18 millimeters in diameter. Then we are to compare the status and the design strength obtained in 1 and 2 and comment on the role of the compression steel in reinforced concrete. For both analyses, we are given the width of beam, the depth of beam, the tension steel, which consists of 8 bars 22 millimeters in diameter placed symmetrically 4 by 4. We are also given the compressive strength of concrete and the yield stress of the steel. If you remember, in the first session of this set of videos, I explained the Maple document that handles the analysis of singly reinforced concrete cross-sections, rectangular cross-sections. If we go back to that document, here you can see analysis of singly reinforced rectangular concrete beams for flexure, and inset the input parameters of the example that I just showed you on screen here, and run the Maple document as a singly reinforced. Maple will plot the results and show us that the beam is in the transition zone, and thus it failed to satisfy the ACI code requirements. And in the ductility plot, you can see here that we have dived into the transition zone. Now, if we take the same beam and run it as a doubly reinforced beam, let's insert these parameters here. This is the template where we are analyzing doubly reinforced concrete beams. So let's insert the parameters of the beam that we are considering, which is 550, 300, 420, 28, 22, 22, 18, 4, 10, and run the Maple document. You can see here that the section is tension controlled. The design strength is printed. Maple printed the plot of the cross section and it showed that we are in the tension controlled zone. So what happened here? And what is the actual purpose of compression steel in reinforced concrete cross sections? Let us think even deeper in this matter. Let's go back here to the analysis of singly reinforced beam cross section and reduce the number of bars in the second layer of tension steel to 2 and run the document to make the beam acceptable according to the ACI code requirements. You can see that the beam now is tension controlled and the design strength is 350 kilonewtons meter. Let's take the same beam and run it as a doubly reinforced concrete cross section. So here we will add 2 instead of 4 and run. So you can see now that the section here is tension controlled and the design strength is 362.55 kilonewton meters. The difference between the two moments is less than 4%. So what is the actual reason for adding compression steel into a reinforced concrete beam? The answer is to increase ductility. The increase in the moment due to the addition of compression steel does not go further than 5%. What we are doing here is we are increasing the ductility of the cross-section in order to be able to add more steel to it. Think of the example that we have just solved on screen. When this beam was analyzed as a singly reinforced cross-section, it turned out to be in the transition zone and thus it failed to satisfy the ACI code requirements because the amount of steel in that beam is larger than the amount acceptable. Now, if we add a couple of bars in the compression zone, we are actually increasing the ductility of the beam, and thus we will be able to add the required amount of steel in tension without violating the requirements of the ACI code. Try solving a couple of problems by hand, and then start trying to create your own templates, because these templates will tremendously cut the amount of time and effort that you need to perform the tasks required from you as an engineer. This concludes the second session. Thank you very much for being with me, and hopefully I will see you in the upcoming sessions. Best wishes.